We'll be talking about the reactions of pyridine. For the nucleophilic aromatic substitution of pyridine, we know that pyridine is more electron poor than benzene. As a result, it's more susceptible to nucleophilic attack. When we react it with a nucleophile, the nucleophile often attacks the C2 or the C4 carbon. This is because this would give you an intermediate where one of its resonance forms is a negative charge on the nitrogen. This is preferred because nitrogen is more electronegative than carbon, so it wants a negative charge more than carbon. For C3 nucleophilic attack, it doesn't have a lone pair in the nitrogen. All the negative charges are on the carbons. So we can say that C2 and C4 attack is more preferred. The mechanism of this reaction is the lone pair of the nucleophile attacks the carbon, either the C2 or the C4, in this case the C2. Once the nucleophile attacks that, there would be more electrons on that one carbon, so then the double bond is kicked out, and so the lone pairs, the pi bonds, are becoming lone pairs to the C3 carbon. This would generate a negatively charged intermediate. This intermediate is resonance stabilized, as you can see from here. The lone pairs could come back into the ring and kick another double bond to the C5 carbon, and that would lead to that one. But these lone pairs can also come back to the ring and kick another double bond, and this would lead to that negatively charged nitrogen intermediate. These lone pairs in the nitrogen would want to come back to the ring again to reform aromaticity. Once it comes back there would be too many electrons on that carbon. So then it would kick out the leaving group, and you would have an aromatic pyridine with a nucleophile in C2. And the lone pairs on the leaving group would then attack an electrophile in the environment to form a bond between the electrophile and the leaving group. Same as for the C4 nucleophilic attack. The nucleophile goes to the C4 carbon. You would have a resonance stabilized intermediate, and the lone pairs would go back to the ring to reform aromaticity, and in this case kick out a hydrogen. The hydrogen is the leaving group, and it would produce a hydride. The hydride would then attack the H+ in the environment and also generate hydrogen gas along with the pyridine with a nucleophile at C4. A sample reaction would be a pyridine reacted to this to form a pyridine with an amine in C2. You would also have a hydride as a leaving group in the first reaction, and that hydride reacts with H+ to form hydrogen gas.
So now we'll be talking about electrophilic aromatic substitution of pyridine. So in this reaction, the electrophile goes to the C3 carbon because a more stable intermediate is evolved. So if you could see here, once the pyridine and the electrophile attach to the C3, a positive charge here in the C2 will be evolved, and through resonance it could be stabilized and it never goes to the nitrogen. And let's compare that with C2 and C4 attachment. Once the electrophile is attached here in the C2 area, a positive charge here is evolved in the intermediate, and that positive charge through resonance can go to the nitrogen here. And same with C4. A positive charge will be evolved in the C3 region, and through resonance it could attach, or the positive charge could go to the nitrogen. And this is not preferred since nitrogen is electronegative and therefore would prefer a negative charge being on it. And let's take a look at the mechanism. So for the mechanism, the pi electrons here in the double bond attack the electrophile like so, and a positively charged intermediate stabilized by resonance will be evolved. And then an elimination reaction will occur. A base will come and attack the hydrogen, which is attached to the carbon that the electrophile is attached to, and the hydrogen will in turn donate its electrons into the ring to allow the ring to regain its aromaticity. And let's take a look at the sample reaction. So for the bromination of pyridine, one needs fuming sulfuric acid, like as you could see here, because the pyridine ring is electron poor, since nitrogen, being electronegative, pulls electrons toward it. So electrophilic addition is not preferred for pyridine.